universal approximation. And I'm going to use my favorite proof method, proof by picture. Okay, so universal approximation. Proof by picture. Now, of course, those of you who are analysis inclined can go and put the meat into this proof. It's not going to be hard to do. You've got to get your epsilons and deltas all in agreement, and you can pull it through. You need to know the analysis, though. You need to know something about convergence in convergence of functions, and so on and so forth, and limits and etc. But the basic idea is that using an architecture like this, if you allow me any number of perceptrons, and if you allow me any number of positive regions, okay, and the ability to combine with and the ability to combine the final, with or in the final layer, then I can basically do anything. Okay? And so here's the proof by picture. So let's try something that looks reasonably hard to do with, linear perceptrons. Okay? So I'm going to have, let's think of a circle. The idea is think of this circle as a generic, boundary, a generic decision boundary that's smooth. Okay, so that's the idea. Now, how do I do this with perceptrons? Well, you can never do it exactly, so that's the idea of universal approximation. With a large enough, multilayer perceptron, large enough means enough nodes in the first hidden layer. These are called hidden layers, by the enough nodes in the first hidden layer and enough nodes in the second hidden layer. I can get arbitrarily close. So let me show you an approximation to this circular region, okay, that this circular boundary that can be approximated with 4 perceptrons. So let me first tell you what's the classification problem, what's the target function. So inside here is plus, okay, and outside we are minus. So outside we are minus. Okay, so we are minus outside. Okay, so here's my first attempt. Okay, so I'm going to put a line here. One of my perceptrons, let's call it W1, with positive inside, W2 with positive inside, W3 with positive inside, and W4 with positive inside. Okay, so what will that implement? That will implement. So if you think of these as H1, H2. So let me label these now H1, what was this? This was H1. This was H2. This was H3. And this is H4, okay? So when they're all plus, so H1 and H2 and H3 and H4, think of the plus as the plus direction of each perceptron is pointing inside, okay? So H1, H2, H3, H4 gives me a positive square region, okay? And so this is just, in this case, it's just one positive region, so I'm just going to have one guy, and taking the OR of that is sort of trivial, okay? You take the OR of that. The OR of one guy is just the guy itself. Okay, but that doesn't look like a very good approximation. Okay, so now let me add a few more. So because what's the error? The error that I'm making, I'm going to call this red region plus, this red region plus. Well, no problem. Give me a few more lines. So this is 4 lines. Now let me add some more dotted lines. Okay, boom. Okay, boom, boom, and boom. Okay, so now again, everything inside. So now I'm classifying as +1 everything that's inside all 8 of those with 8 regions. So let me show you what's the region of error. The region of error now is this small green region in here, this small region here, this small region here, okay, and here, and this small region here, this small region here, this small region here, and there's a small region here. Okay, not drawing too well, but you get the idea. And you say, oh, I'm not happy with that. Okay, let's add another 8 perceptrons. So where am I going to add those 8? I'm going to add those 8 here. 1, 2, 3, 4, 5, 6, 7, 8. And there, you've pretty much got your circle now with 16 perceptrons. Okay, so 16 perceptrons. Okay. Now, you can take this, you can You can basically take this proof by picture to the bank, except that if you want to sit down and do the analysis and get the rigorous proof, you're welcome to do so. Okay, but what do I need here? In this particular example, the 16 perceptrons corresponds to 16 nodes, so the width of this layer will be 16. Okay, and then we compute one AND. We compute the AND of all of those, and the OR layer is pretty trivial. Okay, it's just one positive region. Okay, if I have a very complicated target function with multiple positive regions, okay, if I have 3 positive regions like that, then I might need, I'll need 3 nodes in here, and I might need, 48 perceptrons. Okay, so I'll put 48 nodes in here. And you can see that if you give me arbitrary width here and arbitrary width here, I can basically do anything. That's the content of universal approximation. That's how powerful it is to cascade what? To cascade what? To cascade linear perceptrons. All we're doing is cascading linear perceptrons. Okay. And basically, what is the power that I need? I need the power to cascade linear perceptrons and then pick whatever weights I want on the edges. So what's the power I need? The power I need is 1. Cascade linear perceptrons. And all I need is 3 layers. So 3 cascades. 3 layers, okay, width of first layer corresponds to number of perceptrons in the decomposition of my function of interest, corresponds to number of perceptrons. And the second layer corresponds to ANDs for each positive region. Okay, and then the third layer is just one big OR. Okay. Now, in order to implement the first layer perceptrons, I need to be able to set the weights. So that's the other ability I need, the ability to set the weights on each perceptron. Now it turns out that, I really only need the ability to set the weights in the first layer, which defines these individual perceptrons, because the second layer is computing all ANDs, and the third layer is computing an OR, and so those weights can be fixed. If I wanted to do it that way, but, we can get more flexibility by giving us the ability to even change these weights and do more than just AND in this layer, and do more than just OR in this layer. And imagine the power I get then. Superpower. Okay. Avengers. Okay. So, you can imagine that if you give me this so you can imagine you give me this ability to add as many perceptrons as I want, as many positive regions as I want, the ability to change all the weights, I have a huge amount of fitting power. Okay, so huge amount of fitting power, i.e. approximation capability. Now let's go back to the foundations, and I'm going to ask you, so what am I sacrificing for that? Think back to the foundations. Think back. Approximation versus what? Generalization. Okay. So yes, I've gained a huge amount of approximation capability, but generalization is going to be an issue. What about versus generalization? Question. Exclamation point. You can't escape the theory. And we'll discuss this, question a little bit later. But the bottom line is, the more nodes you give me in this layer, in other words, the more individual perceptrons you give me, okay, and the more nodes you give me in this layer, the more positive regions I'm allowed to use, okay, and then I can set all the weights at will, okay, you are significantly increasing my approximation capability. That's what my approximation capability depends on, which is, what we call the architecture of the multilayer perceptron. Okay. And, imagine now if I go for more than 3 layers, if I go for a 4th and a 5th and a deep network, wow! Okay. Your approximation capability is going to skyrocket through the roof. So generalization, we have to really work hard to get that under control. Okay? You can never escape the foundations. You cannot. Don't try to. Every time you try to escape the foundations, you will fail. Okay? So we're going to have to deal with that. The second question we're going to have to deal with is, for these simple problems, I was able to sort of figure out, how to set the weights, given the weights of the multilayer of these individual perceptrons. Okay? But in general now, I'm going to have to set these weights in order to fit the data. Okay? Because I can't look at the target function and say, oh, that's the target function with this many positive regions and that many hyperplanes to decompose it, and then go and write down the multilayer perceptron. We can't see the target function. We only get the data, so we have to fit the data. And remember, when it came to fitting the simple old perceptron, it was already a very hard combinatorial problem. Okay? And we have PLA and pocket and regression for classification, and you can even use logistic regression for classification, and so on and so forth. Okay? It's already a hard combinatorial problem with just one layer perceptron. So you can imagine how hard it is to fit the data with all these multi-layer perceptrons and all these weights with their interdependencies and so on and so forth. Cascading interdependencies. Okay? This is a very hard combinatorial problem to fit to the data. Okay? And that's going to sort of propel us to introduce instead of the multi-layer perceptron, the cascaded perceptrons, we're going to have to somehow soften this so that it's more manageable. The sign function is essentially what's causing all the problems. Okay? And what we're going to do is we're going to replace this sign function, which is non-differentiable, with the approximation of the sign function, a sigmoid, okay? Essentially tan h. And when we replace these sign functions with the tan h's, give ourselves multiple layers, multiple nodes per layer, the ability to set the weights, we get the multi-layer neural network. So let's erase. I'm going to show you the multi-layer neural network, set up some notation, okay? And we'll call it quits for today. So the notation is very important. So we'll set up the notation and allow time for that to sync because, think about it. We have to keep track of weights in every layer, different layers, and so on and so forth. So we're going to need a very systematic notation, okay? And this notation is, reasonably cumbersome because it has to sort of capture the whole, network. And so it's worth just sitting down and carefully writing down the notation, let that sync, okay, and absorb the notation, which we will use to talk about the nuts and bolts of the multi-layer neural network, or just the neural network. Okay, so let's erase, come back, talk about the multi-layer neural network. Speed erase, bam, 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 bam.